In this video, I want to demonstrate how to draw ray diagrams for lenses and mirrors. The very first diagram that I want to do is just going to be for a plain mirror, the flat mirror that you look in every morning. And then I'm going to go into converging lenses and mirrors. And then I'll end with diverging lenses and mirrors. If you only want one of these diagrams, I'm going to put the timestamp on the YouTube video so that you can click to whichever diagram that you would like to see the demonstration for. So I'm going to begin with a flat mirror. So this is the image formed, again, when you look in just a standard mirror right here, like you can see the ruler in this mirror. Okay, this line here is going to represent the surface of the mirror. I'll go ahead and just draw an arrow. So imagine I'm holding something in the mirror and think, where would you see the image? And so the way this works is light comes and it strikes from all directions. It strikes the tip of the arrow, the light scatters in all directions, and some of that light intercepts the mirror. And so I'm going to draw 3 rays that could come from the tip of the arrow and intersect the surface of the mirror. And so the way you draw ray diagrams for a flat mirror is you realize that the incoming angle and the reflected angle are equal to each other. So then you can get a device. I'm going to use an angle ruler. You could also use a protractor, but you need to measure this incoming angle. And then you realize that it reflects at the same angle. You make sure everything is lined up correctly. One thing that is helpful is if you put arrows on your rays, and so that way you can keep straight which are the incoming and which are the reflected rays. And it should be fairly obvious looking at your diagram, but just in case it isn't, then I'm going to use a blue marker. So when light hits a flat mirror, it scatters in all directions. And you can look at these arrows and tell that they are never ever going to come together to form an image. And yet you see an image anyway, because whatever light strikes your eye and your brain are able to extrapolate backwards and figure out where it came from. All right, off of anything that you see in the room. And then also if that light came off of a mirror, it's going to extend these rays backward. And where they intersect is where your brain is going to form an image. So you extend the reflected rays backward. And if you do your diagram carefully, they should all intersect at the same point, which mine intersected pretty close to the same point. And so this is going to indicate where the tip of the arrow is going to show up in the mirror. And this should also go along with your everyday experience. When you look in the mirror, it looks as if the image is on the other side of the mirror. And it looks like it's about the same distance behind the mirror as you are in front of the mirror. And this is for flat mirrors. So this is how you do image formation and ray tracing for a flat mirror. The next diagram that I want to do is going to be for a converging lens. So a converging lens, an example of that is a magnifying glass. And so you're familiar many times with a magnifying glass. You look through it and you see a large magnified image. What's interesting is you can also form an image on a piece of paper of a distant object. If you look at that, you will see that there's an image of the distant object showing up in that piece of paper. Okay. The first diagram that I'm going to do is going to be for that distant object. And so that's going to be when we've got an object that's farther away than the focal point of the mirror. Before I begin drawing where that distant object image would show up, I want to explain a little bit of how a converging lens works. So for a converging lens, the light that strikes it, the lens is going to be trying to bend that light toward the other light that strikes it. And The focal point is the point at which all of the rays that enter that are parallel to an axis that the lens is centered on will bend to. So if you ever used a magnifying glass to start a piece of paper on fire or something like that, the focal point is where you wanted to put your paper to get it to be the hottest and to light on fire, because that's where all of the rays from the sun would bend to, because by the time the rays from the sun get to the earth, they're pretty much all going parallel. So a parallel ray that, as in parallel to the axis on which the lens is centered, will bend and go through the focal point. This is a reversible process. If we were to take the light source and have it instead be on this side, it would follow the exact same path. And so we can say that a ray that goes through the focal point before striking the lens, it is going to exit parallel to that axis that the lens is centered on. So rays from anywhere. Okay. These are two rays that we know the rules for. A ray that is parallel to the axis on which the lens is centered is going to bend through the focal point. A ray that goes through the focal point before it strikes the lens is going to exit parallel to that axis on which the lens is centered. A third ray that we know the rules for is one that strikes right where the lens and that axis that it's centered on, right where they intersect. And that ray is going to just keep on continuing in straight line motion. Okay, so there are many, many rays that are going to come from an object and strike the lens before being bent. And most of them would be very, very complicated to figure out how exactly the light bends. These three rays are rays that are not complicated, and so we call them the three convenient rays, and we use them in drawing the diagrams that go with the converging lenses and the converging mirrors. All right, I am going to draw a ray diagram for an object that is outside the focal point. I'll just draw an arrow for convenience sake. And the way this goes is we follow the rules for the converging lenses that we just went over. So the first ray enters parallel to the axis on which the lens is centered. When you draw the ray diagram, draw the line, the incoming ray, to the center of the lens before having it bend, and you'll end up with a better diagram. Okay, the second ray that we talked about is the one that goes through the focal point before it gets to the lens. It bends and exits parallel to the axis. Another little tip is if you're drawing these diagrams to make a parallel line, you could obviously measure the distance at a couple points and connect the dots to make sure the line was parallel. You can also just eyeball it and kind of, if you've got a meter stick or even a ruler, it's easy to see if your ruler or meter stick is about equidistant from the axis the entire time. Right, our third ray goes and intersects the axis where the lens and axis intersect. There's our third convenient ray. All right, so where these rays come together is where the image is going to be formed. And you might look at this and be able to determine that it's going to be inverted. A way to prove that it's going to be inverted is to draw that same ray diagram from the center of the object. So I will repeat those same three convenient rays. The first one goes parallel, bends at the lens, and goes through the focal point. The second one goes through the focal point before it hits the lens, and then it bends and exits parallel to the axis on which the lens is centered. And then the third one goes to the very center where the lens and the axis intersect each other and keeps on going straight. Okay, and so we can look at this and see that the center of this object does indeed show up right here, indicating that our image is going to be upside down. And this particular image is called a real image because the light rays really truly go there. They actually converge. When we looked at the flat plane mirror, the image that we did earlier, that is a virtual image because the light rays in reality scatter off of the mirror and go in all directions. You see the virtual image, okay, because of what your eyes and your brain are able to do, but it's not because the light rays actually go there and come together. So these are the rays, 3 convenient rays. Parallel bends through F. The one that goes through the center keeps on going straight. The one that goes through F before hitting the lens exits parallel. And once you have those 3 convenient rays, all of the rest of the rays that come from the top of the arrow have to intersect where the image of the top of the arrow is. We don't know the rules for them, but once we know what the intersection point is, we can draw in a few extra rays and know where they have to end up. When you see an image of something, it takes a whole lot more than 3 rays to form that image because all of the rays go there. If I had drawn this ray first, I wouldn't know the rules to say where it was supposed to end up. So I do my 3 convenient rays, locate the image position, and then I can connect the dots on all of the rest of the rays. The next drawing I'm going to do is for when an object is inside the focal length. All right, so it's closer to the lens than the focal point is. We're going to follow and do those 3 convenient rays, but there's going to need to be a little bit of a twist partway through this. The first ray that we talked about, we can still do. The ray that comes in parallel to the axis on which the lens is centered, bends and goes through the focal point. So far, so good. The ray that goes through the focal point before it hits the lens, there's not actually going to be a ray that does that. You can tell by looking at this. And so, since this is a diagram, we can extend the ray backward. If the ray originated through here, goes through, hits the object. So here's the ray, goes through the focal point, hits the object. This is going to exit parallel. So it's a variation on the theme of hitting the focal point before it hits the lens. The third ray that goes through the center, we can draw that one exactly like we did for the previous diagram. Okay, you can look at those rays and you can tell that they are never going to come together to form an image. All right, and so you need to do the same sort of trick that you did with a flat mirror. You've got to extend the rays backwards. So you take these 3 rays, the rays that exit the lens, the rays that have already been bent, and you extend those ones backward to locate the image position. And they intersect at more or less the same position. So this is going to be where the image is going to show up. And so this is a diagram of what happens when you use the converging lens as a magnifying glass. What you see is larger than the actual object. Here's the object. What you're seeing through the magnifying glass is the image. Here's the object. Here's what you see. Your eye is over here extending those rays backward exactly like it did for a flat mirror. The next diagram that I'm going to do is going to be for a converging mirror. As with a converging lens, it can magnify things right here. All right, you can kind of see the magnified pen. And it can also give you a small upside down image. As you can kind of see in this, there's an upside down curtain. Okay. The first image that I'm going to do is going to be for an object outside the focal length. So again, it's going to be farther away. This is going to be for a relatively distant object. And we're going to follow those same 3 rules. The first ray is going to come in parallel. And if you think back to the lens would bend that ray toward the focal point. The mirror is going to reflect the ray through the focal point, just like this. Okay. The second ray that we talked about is the one that went through the focal point on its way to the lens. This one goes through the focal point on its way to the mirror. Instead of being bent parallel, it's going to be reflected parallel, being a mirror and all. Okay. The third ray is going to bounce off. And the rule we generally say is we say that that third ray bounces off at an equal angle to what it hit at. They all bounce off at an equal angle to what they hit at. If we were to draw a tangent line at each of these spots where the ray hits the mirror, we would see that the angle of incidence equals the angle of reflection for every single one. But it's not as apparent as it is for the ray that strikes the very center. So the way you can figure out where to aim that third ray is if you measure the height of your object, measure the same height down below, we call that the target, and then you can line up the center right here in your target and draw a line. And again, if you draw your lines carefully, they should all intersect, which mine are pretty close to doing. And so this is going to be where the image of the top of the arrow shows up. If we were to draw the same three rays from the center, you would, which I would encourage you to do to try this out, you would see that this image is upside down. And we can actually see that, a little upside down image formed with a converging mirror. Okay, it's not showing up very good, but you can see on the piece of paper an image of what is the window that it's reflecting off of. As with the converging lens, we can draw a diagram for an object inside the focal point. We'll start to see a theme here. For the object inside the focal point, we're going to follow the same three convenient rays. The first one enters parallel, and it's going to reflect through the focal point. Don't let it bother you that the ray has to go through the object. This is a diagram after all. It's not where a ray can genuinely go, but the diagram helps us. Okay. The other ray is the one that hits the focal point before it hits the mirror. In this case, we're going to have to do the same thing that we did for an object inside the focal length for the lens. We're going to have to extend this backwards, draw that line. It's going to hit the surface of the mirror, and it's going to reflect parallel to the axis on which the mirror is centered. The third ray is going to hit the very center of the mirror and reflect at an equal angle, just like this. As with the lens, we see that these rays are never ever going to come together and form an image in real life. So we can extend them back, because when you look in that converging mirror, you do indeed see something, but that's a property of your eyes and your brain being able to form that image. And so we can go ahead and extend that backward, just like this. Okay, they don't intersect quite as nicely as the others did, and part of that is a problem just with the curvature of the lens, makes it so that it doesn't go quite to that center axis that the other thing did. But you do still see an image. The light comes together and forms a great big magnified image over here. It's a virtual image because the light rays don't truly come over here. They truly bounce off the mirror and go in all directions. The last thing that I want to cover are diverging lenses and mirrors, and they only have one iteration of drawing for each one of them. It doesn't matter whether the object is inside or outside of the focal length. A diverging lens and mirror is taking the light that strikes it and spreading it apart. Okay, the converging lenses try to make the light bend toward it, the other light that strikes it, and sometimes it actually succeeds and gets it to come together and form a real image. And when it's too close, as in when the object is inside the focal length, then you're going to get a virtual image, but the light rays are still bent a little toward each other. They just aren't bent enough to come together. With a diverging lenses and mirrors, as you might get from the name, it's making the light diverge no matter what. Okay, so you're never going to have a real image with this. And instead of a focal point, I'm still labeling them F, but they're actually antifocal points. They're points at which the light is going to be bent away from the lens. Okay, So we'll follow the same starts of the three convenient rays like we did with the lenses and mirrors, but now instead of bending toward the focal point, it's going to be bending away from the focal point, or from the antifocal point. So this right here, here's the focal point. It's going to be bending the light away from it instead of toward it. Just like that. Instead of the light going through the focal point and somehow being bent when it hits a lens, it's actually going to aim for the antifocal point, like this. Aiming for that, doesn't quite make it. It's going to be bent and exit parallel to the axis. Just like this. The third ray, the one that goes to where the lens and the axis intersects, is going to just do the same thing it did before. It's going to keep on going straight. Okay, so we can look at these three rays. We can see that they're never going to come together and form an image. And we can also see that they are indeed more divergent from each other than they were before they entered. So just like with the other virtual images, we have to extend the rays back to see where the image is going to form. This one's straight, so this is going to be the exact same line. So then you're going to have a smaller image right here. So those diverging lenses form images that are smaller than the object. So this is for a diverging lens. Now we're going to go ahead and look at a diverging mirror. For our diverging mirror, again, this is a type of mirror that many times you have on a rearview mirror for the car, and it says objects in the mirror are closer than they appear. And it always kind of makes me think of a Far Side, because objects in the mirror are closer than they appear, and then it shows this monstrous eye of a monster. So in other words, a monster is about to eat the car. So anyway, objects are closer than they appear. So let's see what it appears to be. So we have the ray that comes in parallel, just like we have for every one of our drawings. For the diverging lens, the light was bent away from the antifocal point. For the diverging mirror, it's reflected away from the antifocal point. The next ray we're going to look at is the one that is aiming for the antifocal point, just like this. The lens bent the light back, bent the light parallel. The mirror is going to reflect the light parallel to the axis on which it is centered. The third ray is the one that strikes right where the mirror and the axis intersect each other. And it does exactly the same thing that it does for the converging mirror. It reflects it with that equal angle type thing. Just like this. Again, if you put arrows on the reflected rays, it can help clue you in as to which rays are incoming and which are reflected. As with the diverging lens, these rays are never going to come together to form an image, so you extend them backward. Just extends, and if I had drawn this a little more carefully, they would presumably all intersect, and we would see a small right side up image. And so this is also those mirrors that you'll look at. Sometimes I'll have them angled when you're coming up to a corner in a hallway, and then you can look and make sure you're not about to crash into somebody. And so what you see is a small image of yourself and of whatever else is being reflected, and they're all right side up. Okay, so that is how you do image formation with lenses and mirrors, and do your ray tracing diagrams.